Okay. Hello, everyone. My name is Moisis Meonidis, and I'm a PhD candidate at the University of Cyprus, and of course, member of the Rainbow Project. And today I will present you the Rainbow data management and analytics stack through my presentation and via demo. So Rainbow platform is a for-computed platform that simplifies the deployment and management of scalable, heterogeneous, and secure IoT services. Specifically, it provides deployment, orchestration, network fabric, and of course, the data management stack for scalable edge applications. In that direction, Rainbow provides a whole monitoring, storage, and analytics stack that can be used also independently from the rest of the project. So specifically, the monitoring agent retrieves metrics from the fog nodes, running containerized services and user-defined custom metrics, and stores them on the Rainbow storage agents. The storage agents create a unified storage fabric from which the analytic workers can retrieve the metrics for further analysis. Users may either request raw metrics from the storage fabric, or they can submit streaming analytic queries through the analytic editor. And the analytic enabler translates the queries to an executable and submits it to the analytic executor. In case of Rainbow, we utilize a Rainbow-enabled Apache Storm cluster, and the analytic executor utilizes an analytic scheduler as it is selected by the user and places the analytic tasks to the specific workers. Finally, the generated results are stored again on the storage fabric, and users can plot them through the Rainbow dashboard. So in this demonstration, we selected to introduce a distributed application from the intelligent transportation sector. So let us assume that a taxi operator would like to analyze region-based data from its fleet. So it deploys MEC servers in a city section. The taxis generate and publish their data to the MECs, and the MECs perform region-based aggregations and propagate the generated data to the cloud. So in this experiment, we will have two MECs and two taxi workload generators that reproduce the data set, and a cloud server that stores the final results. Among the nodes, the latency will be 10 milliseconds, and the bandwidth will be 10 megabps per second. So the taxi operator would like to know various questions about his application, like what is the overall memory usage of the deployment, which is the CPU rate of a specific MEC node, how many passengers is the company currently serving, and so on. So without needing to reconfigure each application, can utilize Rainbow Analytics Stack to answer these questions. So to perform the deployment, we will utilize a fog emulation framework, namely the Fogify, and specifically we designed and placed the services on specific nodes. So for instance, the analytic enabler, the storage cluster head, the storm master, and the storm UI, the zookeeper, and the dashboard, which is components of the Rainbow platform, will be placed at the cluster head along with the application server. On each fog node, we will deploy a MEC service and a workload generator, which are services of the application. And we will also deploy three Rainbow services: the analytic worker, or in other words, the supervisor, the storage server, and the monitoring agent. As you can see, we have two heterogeneous fog nodes with different processing and energy profiles. The fog node 1 has 2 cores and 2 GB of RAM with up to 8 watts energy consumption. And the fog node 2 has 4 cores with 4 GB of RAM with maximum energy consumption to be up to 200 watts. So if I go to the configuration files, actually is Docker Compose file that includes all services. So we have the services that will be located at the cluster head, which is the zookeeper, the Nimbus, which is the master of the Storm cluster, the Storm UI, the Rainbow Analytic Enabler, and the storage cluster head. We have also some services that are introduced only for this demo, specifically the Analytic Enabler UI and the InfluxDB. And for each worker node, we have a supervisor, a monitoring agent, and one storage server. And of course, we have the application services, the 2 workload generators, the 2 MEC services, and 1 cloud service. So continuing with my presentation, a detailed documentation about the setup and deployment of the analytic stack can be found in the first link, which is the Rainbow documentation site. And more details about the Fogify and its configuration can be found at the second site. And let's go to perform the deployment. So here I introduce some initially generated files in order to create the files for the Fogify deployment. And with that, I deploy the previous mentioned infrastructure right on my laptop. So we have 18 services which run on 3 different nodes, 3 emulated nodes. And the Fogify right now restrict their capabilities and apply the network QoS among them. Of course, we talk about the same services. I mean, the zookeeper, the Nimbus, the Rainbow Analytic Enabler, the monitoring agents, the supervisor, the Storm supervisor, and the Rainbow storage, and of course the service of the application. I will leave here the infrastructure running in order to capture more metrics and to have more interesting results later on. And I will continue again with my presentation. So about the monitoring agent, the monitoring agent is the component that captures the metrics from the infrastructure, and especially the monitoring agent provides methods to capture metrics from the physical fog nodes, containerized services, and of course user-defined metrics. Furthermore, users can update the monitoring periodicity or can utilize adaptive monitoring periodicity in which the system adjusts the periodicity automatically. Furthermore, users may select the dissemination units. By default, we utilize the Ignite exporter, since the Ignite is the materialization technology of our storage fabric. But also users can expose the metrics in different storages like Kafka queues or SQL-based databases. And finally, users can enable adaptive metric dissemination for all or specific metrics. The more interesting part from user perspective is the custom metrics, and users can expose custom metrics via Rainbow Monitoring SDK and its utility functions. For instance, here we have a service that generates the metric with the metric name number of persons, and this metric generates a random value from 0 to 100. And when the service is running, this value will be published to the monitoring agent, and the monitoring agent will store this service to the storage layer. According to the distributed storage fabric, the storage fabric has two components. The storage servers, which are placed on every fork node and keeps locally the monitoring metrics, and the cluster head that instantiates the cluster of the storage agents and creates a unified storage fabric. So the storage fabric also materializes the Rainbow's data placement algorithms. And specifically, we provide two different data placement algorithms. The first one is stability-based placement algorithm that places and replicates the data based on nodes failure profiles. And the second one is the query-based placement algorithm that considers a trade-off between data link quality and data freshness. About the storage configurations, users need to provide initially need to provide two parameters, the discovery and the host name. Specifically, the discovery parameter is the IP or the host name of the storage cluster head. And the host name parameter is the host name of the local storage agent. So the storage agent will be subscribed to the specific master head. At the configuration of the cluster head, we can select the placement parameter to be false or true. This parameter enables the optimizations that I mentioned earlier about the placement algorithms. Of course, we need to set the cluster head parameter as true if the monitoring agent is placed at the cluster head. And we have also two parameters, one for size that restricts the disk size that utilize the storage agent, and the eviction that defines how many hours the agent will keep the monitoring data. And finally, users can also pass JVM parameters to restrict the RAM memory or to enable specific JVM configurations at specific objects. So let's go back to the demo and see what actually the monitoring agent stores to the storage fabric. So when I run this command, I request from the storage fabric two metrics, the CPU utilization and the memory, from a specific node with this name. So as you can see, in every data point, we have many parameters like the metric ID, the entity ID, because this entity is a container, the entity ID is the container ID. We have the entity type, the units, a symbol description. We have also, if this container is deployed via Kubernetes cluster, we have also metadata from Kubernetes like pod UUID, pod name, and pod namespace. And since this metric came from a container, we have metadata from the container, meaning that we have the container ID and container name. We have similar metrics, similar values for the memory. And if I request the custom metrics that I presented earlier at my presentation for the monitoring agent, you will see here we have the metric ID with the number of persons metric name with specific units and a simple description. And its metadata are null because this metric is user defined and has no correlation to any container. So the next component that I would like to highlight is the analytic enabler and its query language. So as I said at the beginning of my presentation, users are able to submit SQL-like streaming queries to the analytic layer. We utilize stream-side framework and its query language, and we extended it to provide Rainbow-enabled optimizations. So specifically, users submit their queries, the system translates the queries and optimizes them by eliminating the unnecessary computations and data transfer, and finally compiles the queries to the underlying streaming big data engine. Actually, the stream site right now provides 3 different compilers, one for Spark, one for Apache Storm, and one for Rainbow-enabled Apache Storm. And of course, as you can understand, we utilized in the Rainbow-enabled Apache Storm. The language provides multiple operators like window operators, cumulative aggregations, filters, and mathematical computations. So for instance, here we have a query that performs average window function on a specific stream and aggregates its results of a window of 10 minutes. We have also a group by statement, and this query will be evaluated every 5 seconds. Here we have a much more complex query in which we have cumulative applications like running average, filter predicates, and mathematical operators like multiplications, etc. And finally, query language provides optimizations via with statement. Actually, the optimizations are focus-oriented optimizations like sampling or placement hints, etc. Of course, users are not users may not learn the language because the Rainbow Analytic UI provides forms and drop-down menus in order users to describe their queries, and automatically translates these forms into the underlying stream-side queries. However, because we ran the demo without the Rainbow dashboard, we created a simple analytic query editor. So we can take these queries and we can submit them to the running system. And here, the first line retrieves the number of persons. This is the user-defined metrics, user-defined metric that I presented earlier, and the system captures this metric from the storage layer and generates a stream of data, and after that performs an aggregation function on top of the stream and aggregate and generates the average of these values for the last 10 seconds, and this insight will be generated every 5 seconds. The second insight computes the overall memory of the cluster for the last 1 second, and the last query generates the CPU rate of a specific MEC node, specifically of the MEC node 2. So we divided the average of the last 5 seconds by the average of the last 10 seconds. As you can see here, we have a deployed artifact to the Storm cluster, and if I go to the Storm UI, you will see we have a submitted topology with the same name, and when we go into that, you will see that we have some transfer data from the storage layer to the analytic layer. We have some spouts, which are the receivers of the system. And we have also some bolts. Bolts are the processors of the storm cluster. And as you can see here, we have the visualized version of the deployment. We have 3 different DAGs, one per query. In this query, you will see that we have 2 receivers. We have some computations, and if you see, we have this computation transfer its data to the to 2 different bolts. This is because the stream side remove the recomputations and data transfer, the unnecessary data transfer. So if I go back to the UI and go to the insights, we can see the results of the queries here. And yeah, here we see the average number of persons for the last 10 seconds. And this query is generated every 5 seconds. The overall memory of the whole cluster, and the CPU rate of a specific node. Of course, the CPU rate is about 1 because we divided the CPU, the average CPU of the last 5 seconds with the average CPU of 10 seconds. So continuing, before continue, I would like to generate the energy consumption of the cluster when the queries are running. So as you can see here, I have the energy consumption of the cluster when the queries, the cluster is idle. And when the queries are running, we have an increased energy consumption. So because we are talking about fog deployment, energy consumption and other fog indicators are metrics that we would like to minimize or to optimize. Towards that, the Rainbow Analytic platform provides also analytic schedulers. Specifically, Rainbow Processing Layer provides multiple task placement strategies that are aware of specific indicators. The default scheduler of the system is the baseline scheduler, which utilizes round-robin task placement approach. The performance and energy aware scheduler provides a trade-off between performance and energy consumption on analytics execution. And finally, we have also a performance and data quality scheduler that maximizes the performance of the submitted queries by handling also issues with monitoring data quality. Next, we will highlight the results of the Rainbow Energy Aware and Performance Aware scheduler. So users at the configuration need to provide the processing and energy profiles of the nodes, and also need to select the energy awareness score. Especially the energy awareness score defines if the scheduler will consider only the energy of the system or the performance of the system or a trade-off between them. So for instance, when the energy awareness is set to be 1, the scheduler takes only into account the energy consumption profiles of the nodes without considering its processing capabilities. When the parameter is 0, it takes only into account the processing power. And for every value between 0 and 1, perform placement accordingly. So if I submit the queries in a Rainbow enabled cluster with the energy aware scheduler, you will see at the Storm UI the Storm scheduler info to highlight energy aware strategy as the selected strategy. And if I go back to my to the running example, you will see here that I have already run the same queries when the energy aware scheduler was enabled, and I captured the energy consumption of the cluster when the queries were running. So as you can see here, we have an energy consumption under 100 watts, while when we utilize the default approach, we had an energy consumption, an overall energy consumption over 100 watts. Similarly, I selected, after that, I redeployed the whole cluster with performance scheduler, with the scheduler, the performance scheduler to be selected. And I redeployed the queries, and I capture again the energy consumption of the cluster. And as you can see here, we have over of an overall energy consumption to be over 200 watts, which is the double of the default energy consumption for these queries. So in conclusion, I presented the Rainbow data management and analytics stack. This stack includes the monitoring agent, and I highlighted how a user can extract user-defined metrics and custom metrics. I provided details about storage fabric, its configurations, and data placement optimization strategies. I highlighted the analytic query language and its expressivity. Of course, I provide details about analytic scheduling strategies, especially for the energy-aware and performance-aware task placement. For this demo, we introduced a representative fog application inspired from the intelligent transportation sector, and I deployed it via the Fogify emulation framework. And of course, we highlighted all the above description via real-time execution and analytic queries deployments. Thank you. If you have any question, I'm more than happy to answer them.
So thank you very much, Moisi. Any questions? Okay, I have a question. Maybe, do you want to say some more details about the energy modeling? Namely, how do you get the energy predictions?
About the energy modeling, actually, users need to provide from the one part, users need to provide the profiles to the scheduler. Of course, in the profiles, users need to select the minimum energy consumption of the node and the maximum energy consumption of the node. And here I have the profiles of our experiment. And at the level of the Fogify, at the level of the emulation, I captured the CPU utilization of a node, and I multiplied the CPU utilization with the maximum energy consumption of the node. Actually, the difference between maximum and minimum energy consumption of the specific node. And we generate the energy consumption of a specific node based on the CPU utilization.
Okay, so it's just the CPU, so you don't count like network or disk I/O.
Yeah, for this demo, I don't count these indicators because in a real life, the energy consumption of a node is about 70 or 80% depending on the CPU utilization.
Okay. But I mean, if a user wants to use a more detailed energy model, then they have to work with the configuration in Fogify, right?
Yeah.
So any other questions? All right, maybe you want to say where this is going to be posted so people can have a look later.
Yeah, actually, I will. Yeah. So the documentation of the Rainbow platform is there. I mean, the Rainbow h2020.readthedocs.io. So in this repo, you will find the documentation for both Rainbow installation and Rainbow's analytic stack. I will also introduce, I will also post here a link to a GitHub repo for this demo, but I don't have, I haven't published the code yet, but I will do it by the end of the day. So for any information you need, you will find them here.
Thank you. And the video, we'll put it on YouTube?
I don't know. I mean, this is a decision that I don't know who need to take.
Maria, about the video, we will certainly put it on the Rainbow's YouTube channel, and it will also be made available through the Rainbow's website.
Great.
Okay, so everyone can access it just through the Rainbow website. And thank you, Moises, for the very interesting presentation and demo.
Thank you. So
thank you very much. I guess we can end here. So wishing you a great weekend. Bye-bye.
bye.
Thanks to everyone. Bye-bye.